So we are going to talk about directional derivatives and the meaning of the gradient vector from a geometric standpoint. Now, it always fascinated me that the derivative of a function in the direction of a particular unit vector is completely determined by how much of that unit vector is parallel to the gradient. If the gradient is the vector of partial derivatives, what does it mean to be in the direction of the gradient vector? What does the direction of a vector of partial derivatives even represent? And you can prove that fact pretty easily in 2 or 3 lines using a dot product and then the fact that the dot product involves the cosine of theta. But that's not a very satisfying answer because the cosine theta kind of pops out from nowhere and there are a lot of hidden steps. So in this video, I want to create an intuitive understanding for where we can look at the directional derivative and understand where that theta comes from. Now, in order to start talking about directional derivatives, we're going to start with one important assumption, which I've written on the board here. Now, when we talk about derivatives, which are essentially talking about slopes when we look at infinitely small changes in the input value, we assume that our function is linear around that point where we're taking the derivative. So this equation here, where z is the output of our function, is saying that we can describe the points in those regions as a linear function or a plane in terms of x times the partial derivative with respect to x plus y times the partial derivative with respect to y plus some constant value. And that constant value is not too important in this case. We really want to look at the changes in the function's value. So this c isn't going to be really important. The important thing is that when we're talking about derivatives, we're looking at an infinitely small region. And therefore, we're able to assume that in that small region, the function is approximately linear. So we can use this equation. Now, the key step that we're going to take when we think about the gradient from a geometric standpoint is we are going to change the coordinate system that we're working with. Now, when we think about coordinate systems, we're often used to the idea of coordinates being in terms of horizontal and vertical values. So if I have a point here, say 5, 3, this coordinate value indicates that the horizontal distance from the origin is 5 and the vertical distance is 3. One other way that we can express that is in terms of two vectors. We can say that the vector 5, 3 is equal to 5 times the vector 1, 0 plus 3 times the vector 0, 1. And this essentially corresponds to the idea of choosing coordinate vectors 1, 0 and 0, 1. And in this case, because those coordinate vectors correspond to unit changes in the horizontal or vertical direction, it allows us to do this very nice and easy description of any particular point in space. But when we're thinking about derivatives, what we want to do is actually modify the way that we're thinking about this coordinate system. So when we're thinking about the two-dimensional input space to our function, the possible values x and y, rather than thinking about them in terms of the basis vectors 1, 0 and 0, 1, we can actually choose other vectors to describe our points. For example, we could choose one vector that looks like this, say negative 3, 2, and one vector like this, negative 1, negative 1. And we could describe any point in space in terms of a combination of those two vectors instead. So what we want to do is take this idea of coordinate systems and find two coordinate vectors to use that allow us to think about rates of change more easily. So what vectors in our 2D input space would be helpful when we're thinking about calculating derivatives? Well, one thing that would be helpful is to know a vector where the vertical change is 0 as we move along that vector. Because that way, if we just think about that vector, it doesn't affect the derivative at all. So we can sort of ignore it when we're doing those calculations. So we might think about when the change in z is equal to 0 for this equation. In that case, what we would need is that x times f sub x plus y times f sub y equals 0 for some vector xy describing the direction we're moving. If we solve this equation, this is just a little algebra problem. Say we want to isolate y. In that case, we get that y is equal to negative f sub x over f sub y times x. So this is a line through the origin, but we're trying to find a particular vector that goes in the direction of this line. So to make things easier, if we try to take everything out of the denominator, we can say that we'll let x equal f sub y. That'll be our definition for x. And then y will equal negative f sub x over f sub y times f sub y, or negative f sub x. And therefore, our first vector is going to be f sub y negative f sub x. So I've taken our first vector v here and written it up at the top of the board so that we can make a little more space here. And before we move on to finding the second vector for our new coordinate basis, I want to take a step back and look at our old standard coordinate system in terms of the vectors 1, 0, and 0, 1, and take a look at some of the properties that it has that make it especially useful to work with. One important property is that the angle between these two basis vectors, 1, 0, and 0, 1, that is a 90-degree angle. They are exactly perpendicular. And the reason that it's helpful to have coordinate vectors that are perpendicular is that these two vectors essentially represent independent directions. And because these two coordinate vectors are perpendicular, they're independent directions, there's actually a really awesome and very useful consequence. If we think about the vector from the origin to our point 5, 3, we can express it as the sum of two vectors. And those vectors are the component of 5, 3 parallel to our first vector 1, 0, plus the component of our vector 5, 3 parallel to the vector 0, 1. We can see that if we connect these two vectors tip to tail, say we take this vector and move it over here, we add those up, we're going to get back to our original point. And one term that's used to talk about the component of a vector that's parallel to another vector is the vector projection. So we would say that 5, 3 is the projection of 5, 3 onto 1, 0 plus the projection of 5, 3 onto 0, 1. When we add up these two vectors, we get our original vector back. And the fact that we can write any vector as the sum of its projections onto the two coordinate vectors ends up being really useful when we think about calculations, where we want to express this vector as a sum of the two coordinate vectors. So what this all means is that these two vectors being perpendicular is very, very helpful. When we go to define our own coordinate system, we want our vectors to be perpendicular as well. So we've defined one vector already here, f sub y negative f sub x. For our other vector, we want to choose it specifically so that it's perpendicular to the other vector. So how do we find a vector that's perpendicular to the vector f sub y negative f sub x? Well, one way that we can do that is by thinking about the line that this vector traverses. We said earlier that the line in the direction of this vector is y equals negative f sub x over f sub y times x. And you might remember from your algebra class that when we look at a line, say that has a slope like this, the line that's exactly perpendicular will have a slope that is the negative reciprocal of our original slope. So in this case, that means that our new line must have a slope of the negative reciprocal of this value here. That's going to be f sub y over f sub x. So we've taken out that negative, and we've also flipped the fraction on its head. So this is going to be our new line, and we want to find a vector on this line. Just like before, we want to take stuff out of the denominator to make it a little easier to work with. So we'll let x equal f sub x, and then we'll have y equal f sub y over f sub x times f sub x will just give us f sub y as a result. And therefore, our second vector, v2, is going to be f sub x, f sub y. And now you might recognize this as the gradient vector. So now we have two vectors that we can use as coordinate vectors for a new system of defining where vectors are located. Now our final goal is to be able to calculate directional derivatives in the direction of some unit vector. So the next thing we have to do is find the change in z for our second vector here so that we can use that to figure out the change in z of other vectors. If we're looking at the vector f sub x, f sub y, we can just plug those x and y values into the equation for z that we have here. That'll give us that the change in z is equal to our x value is f sub x times f sub x, plus our y value is f sub y times f sub y. Again, we don't have to worry about the c because c minus c is 0 when we're looking at changes. Now this will give us f sub x squared plus f sub y squared. But remember that this is the total change in z when we move across a length of f sub x, f sub y. In reality, if we're looking at directional derivatives, we want to think about the change in z per unit length. So in order to do that, we have to divide by the length of this vector. The magnitude of our vector f sub x, f sub y will just be the square root of fx squared plus fy squared. And therefore, our final answer is the square root of fx squared plus fy squared. So I've written that change in the function value per unit length right up here next to our second vector, and we are now in the home stretch, because all we have to do now is think about how our coordinate system relates to a particular unit vector. So if we look at the 2D plane here, and we take our two coordinate vectors, v1 right here and v2 right here, remembering that we defined them so that they are exactly perpendicular. If we take some unit vector right here, u, because our two coordinate vectors are exactly perpendicular, we can write that unit vector as the sum of its projection onto v1 and its projection onto v2. And if we want to find the change in z, we just have to look at the vertical change as a result of each of these parts. Now remember that the change in z, when we go in the direction of v1, is equal to 0. So if we're looking at the projection of u onto the vector v1, this part of u is not going to affect the derivative at all. So we actually don't care about this part. It's not part of our derivative calculation. All that matters is this component. The change in z per unit length, which is the way that we define the directional derivative of f in the direction of u. That's going to equal the change in z per unit length in the direction of v2, square root of fx squared plus fy squared, times the projection of u onto v2. The length, the magnitude of this vector projection here of u onto v2, that is talking about the distance that u travels in the direction of v2. So if we take the distance times the change in z per unit distance, that's going to give us our directional derivative. All that's left is to figure out this part right here. So let's zoom in on this component of our diagram. Notice that we're getting a right triangle as we look at this. This side right here, that's going to be our unit vector u, which has a length of 1. We have our 90-degree angle here, and we can call this angle theta the angle between u and our gradient vector v2. In that case, the adjacent side is going to have a length of cosine theta, since the hypotenuse is 1. And therefore, this value here, the projection of u onto v2, That is exactly cosine theta. And therefore, the directional derivative of f in the direction of our unit vector is equal to this square root, which is the magnitude of the gradient of f, our vector here, times the cosine of theta, which we can also write as the gradient of f dotted with our unit vector because it has a length of 1. And now we finally see our cosine theta coming out of this process not from a dot product, but from the adjacent side of a right triangle. So the way that we got here was starting by approximating our function around the point of interest as a plane, as linear in every direction. Then we redefined our coordinate system. Instead of being in terms of the vectors 1, 0, and 0, 1, we chose two other vectors. First, to make things easy, we chose the direction of zero change, which ends up being f sub y negative f sub x. And from there, there's a very cool geometric fact that we can write a vector as the sum of its projections onto two orthogonal vectors. And therefore, we want our second coordinate vector to be orthogonal to the first. And from that, we got our second vector orthogonal to the first one as being f sub x, f sub y. That's our gradient vector. When we go to look at a diagram expressing some unit vector as the sum of those two projections, the part in the direction of the vector with zero change doesn't affect our derivative. So all that matters is the length of our unit vector in the direction of v2, the vector orthogonal to the zero change line. So that's where the cosine theta comes from, and that's why the direction of the gradient vector actually means something. The gradient vector isn't just a placeholder for the partial derivatives f sub x and f sub y. It's actually talking about the direction orthogonal to the vector of zero change. That's the only direction that affects the value of a directional derivative. And therefore, the directional derivative is determined by how much of that vector is parallel to the gradient.